So I will talk about the Inviscid limit problem for the Navier-Stokes equations, and the purpose of the talk is kind of to give you an overview of the area, what has been done, what can one do and what this problem is. So I will also speak about the joint work with Vlad Vikol and Fei Wang, but on the convergence of the Navier-Stokes equation toward the Euler equation. So, but I will give an overview of many results. So hopefully I'll not, I will keep an eye on time. So hopefully it's possible. So the Euler equations, everybody knows, are incompressible Euler equations are of this form. And we know the basic existence theorem, which is due to Ebin and Marsden, and then later by Temam with a more Sobolev type proof, energy type proof. So if the U0 belongs to a high enough Sobolev space, so in HM, in M is bigger than D plus 1 over 2, then there exists a unique solution in the L infinity HM. And the time depends only on the size of the initial data and the M and D. So yeah, so the simpler proof by Temam, and this is well known. And we also know the Navier-Stokes equations, where we include the viscosity, and the initial data is U0, and if you have a boundary, then we also require that U0 dot n is equal to 0. Then by theory, all theorems of Leray and Hoff, there exists a local weak solution. There exists a global weak solution in L infinity L2 intersection L2H1, which satisfies the energy inequality in a certain sense, well known to everybody in fluids. So the proof which gives the existence of the Euler solutions actually works in RD or the torus also, and gives the same theorem. So if you're in HM and M bigger than D halves plus 1, for also for the Navier-Stokes equations, which are independent of nu. And the basic question, I'll make it more precise shortly, of the vanishing viscosity is, do solutions of the Navier-Stokes equations converge to the solutions of the Euler equations in some kind of sense? Okay, so it's well known that the answer is yes in the case of RD and TD, so in the torus and RD. And these are some references in different settings. And I'll state the theorem of Kato on the next slide. Okay, so here is the version which he proved in 72. So if the initial data is in HM, M an integer, so that's not essential by later theorems, but he had M greater or equal than 3, M bigger than 5, 2 works. So then there exists a time depending only on the size of the initial data, but not depending on U, such that U is a solution which is continuous in HM and absolutely continuous in HM minus 1. And also due to the dissipation term, it's in L2 HM plus 1. And moreover, for every time in this range, the limit exists strongly in HM minus 1 and weakly in HM, uniformly in T. And moreover, the limit satisfies it's continuous in HM and absolutely continuous in HM minus 1 is a unique solution to the Euler equations. So clearly something is not satisfactory, so weak convergence in HM, and this was resolved by the Masmoudi in 2007, who proved that actually the strong convergence also holds in HM by an argument. So here is the proof of the strong convergence in L2. Actually, the most natural proof works. We write the difference of two solutions, U minus U bar, and then the difference satisfies this equation. So clearly, it's a problem. We have U here, because of this, yeah, so U is the Navier-Stokes solution, and U bar will always denote the Euler solution. And we have here new Laplacian nu, so that's why we add and subtract. So we have new Laplacian v, and this we can use as an error term. We put it on the right side. We know that the Euler solution is smooth, so this term actually is nice. It has a small parameter in front. This is a smooth quantity. So we test it with V, and we get energy inequality. So ddt plus this plus that is less than or equal than this. So we also have to put this term on the right side, and we get a nice energy inequality. So ddt VL2 is bounded by new Laplacian U bar. That's given. So we can consider all the quantities related to Euler given. It's only the Navier-Stokes solution which is varying, because of new dependence. So we get nu times the known quantity plus we have VL2 on both sides. So the Gronwall works, and we get O of nu convergence by the Gronwall lemma in L2. So not only the convergence works, but we get O of nu. For once we get, if we take derivatives, the same proof works, but maybe you need to integrate by parts, because if you have a lot of derivatives falling on U bar, you're not allowed to really perform this. You need to integrate by parts. So actually in HM-1, the rate of the convergence is nu to the half. And as you approach HM, you get exponent, and that goes to 0. So these are sort of the rates of convergence. But in Rn or the torus, this simple energy proof works, and we get convergence of solutions. So this same statement or same proof does not hold in the case of a bounded domain. And actually the statement cannot hold because of the mismatch of the boundary conditions. So for the Navier-Stokes, we take Dirichlet. So the solution is actually very small, close to the boundary, while Euler equation allows the tangential slip. So in L infinity, they're not going to be close to each other. So in HM, as soon as the Euler equation is non-zero, we cannot expect the convergence. So actually, the theorem as stated is not true. Okay, so these are the boundary conditions for the Navier-Stokes, and this for the Euler. Okay, so if but we know that for U naught in L2, the solution exists, and this only precludes the convergence in L infinity, but maybe in L2 it would still hold. And this is what we call the Inviscid limit problem, which asks, do solutions of the Navier-Stokes equations converge to the Euler equations in the energy norm? Namely, do we have U minus U bar in the norm L infinity L2 for some small t, but which has to be independent of nu? So it does not have to be all the way to infinity, but it's probably not even true all the way to infinity, but for a short time seems possible. Okay, in this extent, the problem is still completely open. It's one of the big problems in fluid dynamics. So, so again, the answer, if there's no boundary, it's true, but if when there is when we have the boundary, then it's not known. We know that the convergence, as I mentioned from the picture, cannot hold in L infinity. And actually, there has been a lot of statements about what kind of convergence can hold and some sufficient conditions. So Kelliher in 2016 proved that the vorticity has to go to infinity. And it's actually a very quick proof. So if you take the LP norm of the Euler equation of the solution on the boundary, we can just write it as U minus U bar because U vanishes. Then we just interpolate. If this were bounded, and if this were converging to 0, we would get that this is 0, but it's not. We assume that the Euler solution is non-zero, so on the boundary. Okay, so that's So there are other boundary conditions other than Dirichlet. The answer is actually affirmative. So for Navier boundary conditions, you can look the reference Masmoudi-Rosset with co-tangential Sobolev spaces. Also here is one more reference, but there are many more. So Vercelli Spirito or vanishing vorticity on the boundary. So for in the bounded domain, there is a necessary insufficient condition established by Kato in '84, which says that the Inviscid limit holds on the interval if and only if the energy in a neighborhood of a boundary converges to zero. So since we know that this quantity is bounded when we replace with here with omega, this seems like quite feasible to be provable, but it turns out to be nobody was able to verify this condition in full generality because of non-uniform continuity. Yes, this goes to zero for every individual solution as you send this radius to zero, but you have to prove it for every u, and you have to prove it for this neighborhood. So the size of the neighborhood, the boundary is, so the size is small, constant, or you can take it as small as you wish, times nu. So he also proved that the Inviscid limit holds if and only if u converges to u bar weakly for every individual t. So weakening the topology does not help with the convergence. So it holds uniformly if and only if converges weakly, and it's kind of easy to verify. And one more thing, the proof for Rn does not work here because when we integrate it by parts on the left side in the energy, yes, we get a coercive term, but this is the term which is as powerful as this one, so it cannot be absorbed and cannot be controlled. And one slide proof of the Kato's criterion, because it's very beautiful. So the idea is to correct the solution of the Euler equation to be zero at the boundary. So we introduce a corrector, phi, which matches with the tangential component of the Euler. And you make it something like on this graphic. So plot it for t equal constant, x1 equal constant. Then it starts with a minus Euler. So you want the sum to be zero. And then you have to make the average zero. So these parts have to cancel so that phi2 would be compactly supported. So that's sort of the graphic of the corrector. And alpha is kind of chosen in some optimal way. So after subtracting writing the equation for u minus u bar and testing it with u minus u bar minus phi, this term turned out to be the biggest possible, one coming from the dissipation, d2 u1, d2 phi1, and the other one from the nonlinearity, which is u1, u2, d2 phi1. That's for the half space. Something similar happens for the bounded domain, but these are the main terms. And on this term, we apply Poincaré because u1, we are looking at this integral in a small neighborhood, alpha. So small alpha helps. So here, small alpha is good. While on this term, we want to just use Cauchy-Schwarz. So D2 produces alpha there. So here, alpha would be great if it were large. So there is a balance, and the balance is achieved when alpha is a constant times nu. And so we obtain these two terms, and very short argument then, if you ignore all the other terms, tells you that if and only if you have Inviscid limit, if and only if the integral of the gradient u squared vanish. The other terms are all of the lower order. For instance, whenever you have d1 phi1, that's of lower order because you're not differentiating in this direction. Direction d1 f1 is small. Okay, so that is the short proof. Of course, that the proof is longer because one needs to check every term. And also how to extend to the curved domain, it's not trivial. So this condition seemed like it's a borderline condition. So for instance, if you allow T to be nu dependent, then it holds. So it seems like just if you tweak something by a little bit, you get it, right? But so it's sort of a marginal condition, yet again, nobody was able to verify it. So there, however, there have been several formulations of like different conditions. For example, Wong's condition is Xiaoming Wong. It's the same, except that you only take the tangential component. However, we have to take the neighborhood to be larger. So the idea of the proof is that this is one of those two bad terms. So we apply Poincaré, we get D2 here, D2 there, and D2U2 is tangential. So that's the idea. And so then condition by Kelliher is we can replace the gradient U squared with the vorticity with the same size as Cutoff, so small constant times nu. And the proof is by replacing D2U1 with omega, and then we have D1U2. So here you can just integrate by parts. You put D1 first here, and then D2 there, because U2 is 0. And this term is lower order, because it's D1 phi1. Okay, so that is the... then there is a more involved condition with convergence in H1 prime of the gradient, which again can be proven by integration by parts. And the enemy is always this boundary term which arises, and then this has to be dealt with in some way. So this is the condition in H1 prime. And there is also a Bardas-Titi condition, omega minus omega dot n, that going to 0. Two more or three more. So the Konstantin-Elgin-Ignatov we call is that the U1 times U2, so this term is equicontinuous at y equals 0 for some small constant C naught. So U1, U2 is a Navier-Stokes solution. So it's again a sufficient condition, so for regularity. And there is also a compressible Cutoff criterion, which is a little bit more complicated due to Sur, which says, so here we have the Cutoff quantity, but then we also have to send two other quantities that have to go to 0. So it's a little bit more complicated, but in the same spirit. So for compressible, the question is suppose harder. All right, here it's also a condition joined with Konstantin and Vikol some time ago. For monotone data. So monotone data, maybe it's not a bad class to try to prove the Inviscid limit. However, it's also open for the monotone data. It has to do with Prandtl. So Prandtl tends to behave better for monotone data. Yet again, it's an open problem. And our condition was that monotonicity of the Euler trace. So this is actually fine, because we can assume things on the Euler, but there is also a condition on the tray on U. Where is it? Yeah, here. Okay, so omega greater or equal than 0. So this is the sufficient condition for the regularity. If the Navier-Stokes vorticity is bounded from below on the boundary, then the Inviscid limit holds. So that seems like plausible to check, but again, seems like just a sufficient condition. This can be relaxed into 1 over nu type sufficient condition, and almost a constant, just a little bit of nu, but basically lower bounds 1 over nu. However, lower bounds even in 2D are very tough to obtain, or upper bounds. So if one wants to obtain Navier-Stokes bounds in terms of the viscosity, the best known bound is exponential. So e to the nu, and that's another open problem in the theory of Navier-Stokes equations, which is connected to the Inviscid limit problem. So i.e. proving an algebraic bound on omega in terms of viscosity. Okay, so these were sort of conditional results, which could be verified in certain special situations, so that they're useful. And but there exists an unconditional result, and I'll give you an overview of this. So Sammartino-Kaflish, they proved the Inviscid limit holding when the initial data is analytic, and this is YDY analyticity. Uniform analyticity on the boundary seems too much. Clearly, those spaces cannot be used because we cannot expect L-infinity convergence. So we should not use uniform convergence spaces at all in the proof. So one of many ideas they had was to use YDY analyticity. And the main tool is the parental expansions. I'll speak about that in a few moments, what that is. And then the energy method was later given by Wang and Zhang. Then Maekawa had the following conditions. So the Inviscid limit holds if the vorticity is supported away from the boundary, which and 3D version was also obtained by the reference there. So if vorticity is 0 close to the boundary, then the Inviscid limit holds. Gwen, they found an alternative proof of the Sammartino-Kaflish without parental correctors. And our joint work with Vicol and Wang is that the Inviscid limit holds if the initial data is analytic close to the boundary and Sobolev, H4 Sobolev away from the boundary. So this generalizes these two results because if the verticity is 0 close to the boundary, then it's also analytic. So, and of course, if it's analytic, then it must be Sobolev. So it contain the other two, and I'll get to just setting up the spaces, I believe, later on in this talk. The Fei Wang proved the 3D version of this result. So our version was the 2D for the half space, and the difficult generalization to the curved domain was obtained by Bardos, Gwen, and Titi. But that's for the curved domains and initial data again, analytic close to the boundary and Sobolev from the boundary. Okay, maybe some other, I cannot mention every possible result, but there is also some special symmetries where we actually know that the limit is attained. So you can see this estimate, or better see the review paper by Maekawa Mazzucato, which contains all the results up to 2018 review. So maybe a few things about the parental expansion and about our result. Yeah, so that's for the rest of the talk. So the parental expansion, this was physically introduced by Parental a long time ago, but first time I think was very usefully, in a useful way applied in the mathematical setting in this Inviscid limit. So they looked for Navier-Stokes solution as a asymptotic expansion of the Euler being the 0th order term. First order term or corrector would be the parental, which is some fixed solution, epsilon independent, evaluated at y over epsilon. So, and then an error. And the idea is to actually, their idea was to use this as an ansatz in the Navier-Stokes equations, write the equation for the error, and then evaluate it or estimate it in some space. Okay, so if you replace this ansatz into the Navier-Stokes equations, we obtain they satisfy a parental type equation. So parental is one of these equations which arises in connection to the Inviscid limit, and the boundary conditions are matching with the Euler or negative Euler, like the Kato corrector and this So it turns out that the scale we have to take is square root of nu. So if you plug this, due to two derivatives in y, you will get epsilon squared. So epsilon squared has to be nu, or epsilon must be square root of nu. So the parental equation for the corrector looks like this. And the second component is computed as an integral from infinity to y of the dx of up. And it is convenient to homogenize the boundary condition at y equals 0, because the way it's set up, it has a 0 value at infinity, but non-zero at 0. So to actually use the existence theory, then homogenize by this change of variable. And we obtain the classical parental equation, which looks like this. And so the parental equation has the dissipation term, which does not contain the x variable. So that's a difficulty. The second difficulty of the equation is that there is no evolution equation for v. Actually, v is obtained from the integral of up. This may seem like good news, but unfortunately, there's a loss of derivatives. So the equations are actually quite tricky. And there has been a huge progress in the progression of theorems for the local existence, which maybe I'll just pass on right now. But for example, for analytic data, there exists a solution, and this result has since been improved to Gevrey 2 by Gevrey, Masmoudi, and not the TA. I think I'll misspeak. So the TA and Gevrey, I think initially. Okay, so that's the best result. But for analytic data, there exists a solution due to derivative loss. So analyticity can help you with the derivative loss there. So subtracting the parental equation from the Navier-Stokes, one gets the following system, which is slightly complicated, but it's sort of a Navier-Stokes type. So it has a Navier-Stokes structure with epsilon in it, so that's good news. Then it has two linear terms. Then there is an equation for v and the divergence condition. And the second difficulty, besides being slightly messy, is that the condition for v is non-homogeneous. So g is something given. So we have a non-homogeneous condition for the second component of the velocity. And then looking at this equation, one realizes that first, we are not solving it in L2. So we cannot hope on Sobolev cancellations. Number two, we have a derivative loss. So there is a dx here. And to compensate for the derivative loss, we have to use analyticity. And then another observation is that uniform analyticity cannot be used. So we have to use y dy analyticity to eliminate the loss of derivative in this equation. And this is what Sammartino and Kaflish did. Okay, so these are, oh yeah, I forgot even the forcing terms. There's also complicated forcing terms, which we need to check. They have a certain special behavior to be suitable for y dy analyticity. So one needs to check certain smallness, that this epsilon is not carried around. So there has to be cancellations, in quotes, cancellations or compensations. So there is also a negative result on parental expansions. So Grenier and Gwen, they prove that L infinity instability of parental layers holds, which means that if we think that the parental equation is a good approximation for the Navier-Stokes minus Euler, it may be, but not in L infinity. So this does not contradict the Inviscid limit, because anyway, L infinity is a tricky space, so one should work in L2. Okay, so a few words about our analyticity Sobolev Inviscid limit and then validity of the parental expansion. So to state the analyticity Sobolev result, one needs to do this analyticity. So one should use pencil shape if the actually pencil shape if the function is analytic all the way to infinity. But if it is Sobolev away from the boundary, one should actually then let the Sobolev radius go to 0, and then somewhere here the parental has to pick up. Of course, there cannot be a sharp cutoff because one cannot expect to work in two spaces with one regularity on one side, the other regularity on the other side. So the regions have to overlap in some sense. And the norms are the following. So the norms are L1 in the transversal variable. So in this here, we are taking L1, meaning we are integrating this plus this and taking supremum. So that is the L1 component of this. In the perpendicular direction, so in the tangential direction, we use the Foyage-Temam approach to analyticity, or one uses the partial Fourier transform approach. So in the tangential variable is the partial Fourier transform because there is no boundary, and then in the transversal direction we use L1 type norm. And the total analytic norm is then supremum over all mu's up to certain things. So this is this fuzziness of the norm. Not only that, one needs to take it's a technical thing. So up to derivatives 1, there is no weight, but there is a time weight required for the highest derivative. So the reason is just technical. So this, because it's L1 based, it actually allows the growth of the vorticity toward the boundary. So the vorticity can actually grow. So it's not like analyticity is taming the solution, but they can still grow. Kind of running out of time, so I have 2 more minutes. Let me quickly at least go to the idea. So there is a Sobolev norm, there is an analytic norm, and then we add them up to get the cumulative vorticity norm. And that's the theorem. So first one proves that this sum of the analytic norm and the Sobolev norm is uniformly bounded. And then, so if it's bounded at the beginning, then it's bounded for all positive time. Once you have that, then you get a vanishing viscosity statement. So the Navier-Stokes equation has to converge toward Euler. And the main trick actually turns to Cutoff. So basically we prove that once you have the boundedness, omega can be actually uniformly bounded. So from L1 we go to L infinity. And then we use the Cutoff criterion. So in Cutoff criterion, you can, without going through the details because I don't have time, but basically split into close to the boundary and away from the boundary. Close to the boundary, apply analyticity. Further away, it's no problem because we have nu. And without having time, this converges with a rate actually. So there is even a positive rate, which gives you a sense of optimism that things could be approved, although nobody was yet successful. But yeah, there is actually a positive rate, which seems to indicate room, but seems like unexplorable type room. The rate of convergence is all new to the quarter. Maybe one last comment is that the parental expansion can also be obtained. I'll not go through the details. I knew I was preparing too much. But so the result with Vlad and Fei and Trinh Nguyen is that actually the parental expansion holds with the rate C epsilons. So without parental expansion, you get rate epsilon to the half, and then actually the parental expansion then increases the rate. Okay, so I'll stop here, and thank you very much. I think I'm right on time, right?
So thank you very much for your very interesting talk. So are there some questions, remark? Yeah, it seems to be not the case. Okay, yeah, you have.
Hi, Igor. So,
Hi.
Speculative questions. Do you have any opinion about the validity of the conjecture that you stated initially? Or do numerics validate or say anything about it?
Yeah, it seems that I mean, it seems that plausible that it is true. So I think it's more likely than not for a very short time it's true. And for the long time, I saw some numerics which indicate like if you have velocity going toward each other. I saw the numerics that actually it does produce there is a production of the vorticity, the boundary, which actually goes into the interior. So it's not expected that for a long time that it would be true. So one gets creation of the vorticity is an expected phenomenon. But yeah, there is nothing wrong with this being true for short term. But it's one of these things like similar to the regularity of Navier-Stokes. Is it true or not? It's very hard to say. So it seems plausible, but we don't know.
Thank you.
Yeah, I don't have good intuition. I would say more likely than, I mean, I tried hard to prove it, so I think I try to believe it's true by tweaking the cut. Just because the cutoff criterion is so borderline, it seems like it should be true. So that was sort of why I thought maybe.
Let me just make a question to this an observation with respect to this question. I don't think that given both the physics, like experiments and the numerics, you expect the limiting, in general, the limiting solution to be strong. And that makes the cutoff criterion as it stands practically useless, because it assumes the solution, the limiting solution for Euler is H3, okay? Or as regular, more or less as regular. That's where you expect the solution, the limiting solution, to be weak and probably involve things like vortex sheets in the limit, or other irregular things. So you need so in some sense the Prandtl idea, this is all for very smooth limiting flows which you don't expect in general. So you expect.
Yeah, I was commenting on the smooth solution. So assuming that the Euler is smooth, do we expect the Inviscid limit to hold? Yeah.
Exactly.
If the Euler is rough, then yeah, I don't think so.
And you don't expect physically the Euler solution to be smooth in the limit. That's the point.
Yes. But assuming that the Euler solution is smooth, and then on the full extent of the interval, one would not expect the Inviscid limit either, but that's basically by just saying it. But I think I would phrase it where one could be optimistic is assuming that the Euler is smooth, and then there exists a smaller time which is new independent. I don't think that there's anything wrong with Inviscid limit being true, but that's a matter of opinion. But yeah, I totally agree with you. If the Euler solution or Euler solutions in general, they don't look smooth, we have all kinds of strange solutions, right? So then one cannot expect vanishing viscosity to be true.
Okay, so are there some questions, remarks? It seems to be not the case. So I just little remarks, nothing deep. About this compressible case, because there were also results for this vanishing limit by Masmoudi, let's say, when you go from compressible to Euler for, let's say, Dirichlet case, and probably.
Oh, you're right.
Yeah. And then, of course, for the case of Navier type of boundary condition, there are series of works. Yeah, but this is different. Yeah. This is.
Yeah, with compressible, I'm not so familiar.
Yeah.
I think he had like a joint limit, like Mach and Inviscid limit or something like that.
Yes.
So that's paper I didn't. Yes, I'm aware of it. Yes. Yeah. Thank you for pointing out. Yes.
Yeah, and there are some Inviscid limit by Eduard and Antonin and so on, and all these groups. But this is with Navier type of boundary condition. This is different. This is different world. Yeah, let's say. Okay. If there is nothing, so thank you very much. Thank you very much.
Thank you.